Good morning. Thank you everyone for being here. We're getting this morning session started with Francisco Guinea, who's talking about properties of bilayer graphene. Francisco is very well-known theoretician, mainly working on graphene, and I'm very eager to hear what he has to say today. Thank you very much.
Thank you. I'm very glad to be here in this very historic place and in this very exciting meeting today. I will work mostly on these recent discoveries on twisted bilayer graphene. Many of you have heard about them already a number of times, but I will go through them briefly at the beginning anyway. These were the famous experiments which were announced in March 2018 in the March meeting and published simultaneously in Nature and in ConMat and posted in ConMat. And the thing was that the group of Pablo Jarillo Herrero at MIT discovered that by twisting one graphene layer with respect to another, so the sample was just a graphene bilayer, but not a garden variety, a regular graphene bilayer, but a bilayer where the two layers were twisted relatively to each other by 1 degree, about 1 degree. The system shows superconductivity, insulating behavior on a very complex phase diagram. It immediately became a sensation. A lot of people have been working on that. This is a very old slide I have from about a year after, or at least the discovery, and it shows the number of people, the number of communities interested in this problem. A lot of people from the 2D community, from optics, from quantum materials, and so on, immediately moved into this field, and it has become a hot subject ever since. But let me backtrack a little bit, because the whole this study started way back, and there was like a phase transition in the study of graphene with the advent of boron nitride. I mean, in this paper in 2012, it was discovered that boron nitride, which is a well-known wide gap insulator, monolayers were perfect, or systems with a few layers were perfect for encapsulating graphene, and in such a way that graphene preserved very well its very nice transport properties and so on. And after this paper, everything changed in the study of graphene and other 2D materials. You may have heard of these two famous Japanese researchers from Tokyo. By now, they are the best, probably the most cited researchers in the world, and probably with more citations not than most of the total number of Nobel Prize winners in physics, probably. The reason being that they produce excellent boron nitride, and they provide it for free to the laboratories they think they deserve receiving it. And the only condition they ask for is to be in the paper. And as I said, that means that these two guys are by far the most cited scientists in the last years and probably ever. Okay. People started to play with boron nitride and graphene after this interesting discovery. These are old papers. The thing is that the lattice constants of graphene and boron nitride are close, but very, I mean, they differ by only 2%. And because of that, you create large moire patterns where the unit cell is on the order of 10 nanometers or more. And they are like metacrystals, larger crystals. This is what I mean. So you see that depending on how well aligned is boron nitride and graphene, this is when they are perfectly aligned, you see a pattern emerging. This is a bit of a cartoon. The pattern is much larger than that. And this pattern defines for you new periodicities, and it's what I said, a metacrystal. This is the best you can get, and and that motivated a lot of interesting research, because if you manage to align graphene and boron nitride, which is something experimentalists can do, then you have this large metacrystal. And then, you, for instance, you can probe what was way back already suggested, what's called the Hof Starter Butterfly. if you apply a magnetic field to electrons moving in a lattice, and the magnetic field is large enough that you have a quantum flux, quantum unit of flux per unit cell in that lattice, you have an electronic spectrum which is unlike any other spectrum you find in nature. It's not a set of discrete levels, it's not a continuum spectrum like in a metal, it's a fractal. And that is impossible to achieve with normal crystals because you need magnetic fields in the order of thousands of Teslas. But you can do it in a metacrystal defined by a moire like the ones I am talking to you. These are the famous Hof Starter Butterflies, which are, as I said, what they indicate is that the electronic levels in your sample build some kind of fractal pattern. And these are the numbers. So the unit cell, in the case of perfectly aligned boron nitride and graphene, is the lattice constant is about 12 nanometers. That includes about 5,000 carbon atoms. And in order to fill up one band in this periodic system, you need about 10 to the 12 electrons per square centimeter, which is reasonable. And in order to have a magnetic field such that you have a quantum unit of flux per unit cell, is about 5 Teslas, which is quite within the range of what can be achieved in many laboratories. Now, as a theorist, I have also to highlight that it's a very nice system because the fact that the unit cell is so large allows you to make very many approximations. Basically, you can work with the same Dirac equation you apply to graphene, and all these bands you create in this metacrystal can be described by few parameters, and you can do a lot of nice calculations, and you can show that you can open gaps, which is a feat not easily achievable in graphene. You have extra Dirac points and things like that. Okay. Now let's go back to superconductivity in graphene. The group of Pablo Jarillo Herrero was trying to make moire patterns by a different route. The thing is, instead of aligning graphene with a substrate whose lattice constant was close to the graphene, they thought, well, maybe one can make a moire by rotating, by putting two graphene layers one on top of the other, but not perfectly aligned. And I mean, the field has exploded. These are some recent experiments. We are already at the stage where devices can be made using this new phase diagram of twisted bilayer graphene. It's a very highly competitive field. I just see that these are two groups reaching, I mean, making the same, basically the same process of junctures at ETH and at MIT. Now there are even squeeze, and people have gone from twisting 2 layers to twisting 3 layers, 4 layers, 5 layers, and all of them seem to show superconductivity, insulating phases, and so on. So it's a very interesting field, growing rapidly and full of surprises. Beyond the first surprise, the experiments, which already were a big surprise for everybody. So, and nowadays, going to very, very low temperatures, people have noticed something even less expected: superconductivity in regular graphene samples, in tri-layers and bilayers with no twist at all. You have to go to like 50 millikelvin or so. I mean, the critical temperatures are in between 50 and 100 millikelvin, but nobody expected superconductivity in pure, perfect, without twist or anything, graphene samples, and it turns out that there is superconductivity there, even if you have to go to very low temperatures. And one of the reasons this topic is interesting is because the phase diagram shown by these twisted graphene layers is somehow related to the phase diagram of what is typically called strongly correlated systems, which were famous way back, like the superconducting cuprates, the heavy fermion compounds, the pnictides, and so on. all these systems show the coexistence of superconductivity and magnetic phases. It's assumed, or it has been proven experimentally, actually, the Cuprates, that the superconductivity is not conventional at all. and the field of strongly correlated systems has been a wide open field in condensed matter physics for years. And typically, it is assumed that the superconductivity is coming from the proximity to a magnetic phase. That isn't unclear whether that thing survives in, the same mechanism applies to twisted bilayer graphene. Here I'm trying to show some experiments in carbon-based compounds which show things like superconductivity or insulating phases. And there are some, especially the so-called graphite intercalation compounds. It was known that they were superconducting up to 10 kelvins or so way back. But and these are basically heavily doped graphene planes because they are surrounded by metals, alkaline metals or calcium. And these metals donate a lot of electrons to the graphene layers. And then when you apply a strong magnetic field, you also see signs of some kind of magnetism and things like that. And there is the issue that the Fermi velocity of graphene changes a lot because of interactions if you probe it in well-designed and very clean samples. But in all these cases, the carrier density of the graphene layer was very high, and and in the case of graphene intercalation compounds, it's not a carbon-only compound at all. It's crucial to have the metals intercalated. Okay, this is what I mean. This is what happens when you rotate one graphene layer with respect to the other. So you see that there are patterns like the patterns you have when you rotate graphene with respect to boron nitride. The only difference is that there is no limit to the possible lattice constant of this moire. Here you can have moires much larger than the ones you can achieve in the case of graphene, because when you put graphene on top of boron nitride, you cannot avoid this mismatch between the two lattice constants, the 2% mismatch. Here there's no mismatch, so you can make moire patterns as large as you can get. Having said that, it is interesting to know that here, this is not a real moire pattern. Not all the blobs you see in the picture are equal. The two lattices are not strictly commensurate. That's something we all overlook and consider this thing a moire pattern. Strictly speaking, it isn't. How important that difference is, nobody knows for sure right now. Okay. So actually, Pablo Jarillo Herrero was motivated by some interesting theory which already showed way back that there could be very narrow bands in this setup, a graphene layer rotated with respect to another graphene layer, provided that the twist angle was about 1 degree or less. There were interesting calculations which many people, including myself, thought very academical, because we thought that it was very difficult for such a system to be fabricated in nature, but it could. And there were some experiments for larger twist angles, like these ones from Ivan Rey's group, which showed that indeed there were peaks in the density of states, suggesting narrow bands and so on, as you approach these magic angles. And what is happening, as I'm a theorist, I would like to explain it a bit better, is that you have two very clean graphene layers, one of them rotated with respect to the other. So you have the electrons are well described by plane waves. And then from time to time, one of the electrons, which is moving in one layer, tunnels into the second layer. But because of the specificity of the band structure of each graphene layer, this plane wave shows up in the second layer as a superposition of 3 plane waves, not as another plane. Even if momentum is conserved and so on, it turns out, if you make the calculations right, that this initial plane wave becomes a superposition of 3 plane waves when it tunnels into the second layer. Then it tunnels back to the first layer and it becomes 9 plane waves. So the system rapidly becomes very complex, and it's even more so the smaller the twist angle is. And this complex interference process is what is responsible for this large change in the spectrum of the system. And these are the so-called magic angles. So this is one of these narrow bands in twisted bilayer graphene, and this is what happens as you change the angle. Eventually, it becomes incredibly narrow. The width of the band is a few millivolts. And then when you pass this so-called magic angle, the band becomes wider again. So you have to tune a bit the twist angle, and that has been achieved by experimentalists. But if you do it all right, you can have very narrow bands, high density of states, and then electron-electron interactions, electron-phonon interactions can become very relevant. These are early calculations we did, and let's see if this is this famous flashback, which is scale up here. And it's also remarkable because there are flat bands in the cuprates and in the heavy fermion systems, of course. But you have here a large unit cell, and interestingly, depending where in the flat band you are, the charge distribution is very different. For instance, in the heavy fermion systems, which contain elements like cerium or uranium, there are flat bands, but these flat bands are basically located in F orbitals in these elements, and they are flat because they interact, I mean, very little with similar F orbitals in other unit cells, but the bands are always pinned to the F orbitals. Here, there's no orbitals to pin these flat bands. The bands are flat, but they are distributed in different ways depending where in the band you are. And this is the same picture again. I mean, 2 different points in the same band show totally different charge distribution in this large unit cell, which is for this twist angle in the order of 10, 12 nanometers or so. That and then for very low angles, the situation becomes very complex, but then you have many Dirac points. The topology of these bands is much more complex, in fact, than the topology you have in topological insulators or systems like that. Now, where the magic angles come from is still an open question. These are 2 papers discussing the issue where we did some calculations way back, and this group in Harvard put the whole analysis on firmer ground later. And the point is that these flat bands have some resemblance to other flat bands well known in condensed matter physics, and those are the Landau levels you have in any metal, especially 2-dimensional metal, in a magnetic field. So graphene seems to be a material very far from a simple metal in a magnetic field, especially because the bands are derived from highly localized p orbitals, p-set orbitals on the carbon atoms. But nevertheless, the flat bands which come out of these calculations for twisted bilayer graphene, they do resemble somehow the Landau levels you have in a regular metallic 2-dimensional system in a magnetic field. And in that respect, I want to emphasize that in these better studied systems, strongly correlated systems, these flat bands come on one hand, as I said already, because they are derived from highly localized F orbitals in uranium or cerium or whatever. And in addition, the bands become even flatter because then as these systems are close to magnetic transitions, the electrons are dressed, they have to drag along, carry along magnetic excitations, and then they become even heavier. And that's why they have That's why you have narrow bands in heavy fermion systems. But here, the interesting thing is that you neglect total interactions in the calculations I have mentioned to you before. You just plug in parameters for non-interacting electrons in graphene, the smallest of which is about 100 MeVs. And out of the calculation, you get bands which have a width below 5 MeV, which is still quite mysterious. Okay, I mean, there is another topic related to this angle studied at MIT and other places, and that is what happens for very small twist angles. That's very interesting, but I think I will skip that. I mean, so the people by now have produced systems where the rotation between one layer and the other is like 0.2 degrees or something like that. They are completely different from the ones I have discussed already, and they are also very interesting. But let me go back to twisted bilayer graphene, where the twist angle is in the order of 1 degree or so. As a theorist, I was very interested into the topic, and the many other theorists as well. And this is a kind of slide to show the richness of the subject, because it's like this proverbial tale about the elephant described by blind people. We theorists are describing twisted bilayer graphene in very different ways. You can think of it as some kind of Hubbard model, which is the traditional analysis made for strongly correlated systems. You can think of twisted bilayer graphene as a set of Landau levels, which is what you do when you study electrons in high magnetic fields. And you can notice that there are peaks in the density of states, and then in 2 dimensions that were known, those are the Van Hoff singularities, and you use those Van Hoff singularities to guide your theoretical analysis. And all these approaches and more have been described in connection with, or have been used in connection with twisted bilayer graphene. Let me also mention that in order you have flat bands, and a typical way you study them is by defining localized Barnier functions, and then you go to a local basis and you describe the interactions in a local basis and so on. That is there are very subtle problems when you try to define your Barnier functions in twisted bilayer graphene. That's called the obstruction. And this is now a whole new field in topological materials, which materials are obstructed and which materials are not. And one of them is twisted bilayer graphene. So in a few words, the problem with is that these bands in twisted bilayer graphene, like Landau levels, they are topologically non-trivial, and because of that, mathematically, the Barnier functions you can define do not decay exponentially as a nice local atomic orbital. They have a power law tail, and how relevant that power law tail or not is the whole gist of this obstruction problem, which is being intensively debated by all theorists interested in topological materials. Okay, so now, but what I have tried to explain to you is that there are flat bands, definitely, that implies that interactions are important. So here there is a description of different interactions. The nice thing of having these very large unit cells, in this case, these unit cells contain about 10,000 atoms, is that you can use precisely that number, 10,000, as a large number, which allows you to classify the interactions depending on how the energy scales associated to those interactions scale with this number n. And it turns out that the leading interaction, which is the long-range Coulomb interaction. And this effect is particularly important because, as mentioned already, the charges you induce when you apply a gate and you increase the number of carriers are not uniform within the unit cell. For instance, in regular graphene, you can apply a gate and you put more electrons into the bands, but the, the charge density associated to these extra electrons is uniform and is perfectly compensated by the potential created by the gate. Here, you create new charges because you are turning on a voltage, a gate. But in addition to a constant potential, you have a periodic potential within the unit cell, which is large and which is unavoidable. I mean, it's related to the particular topology of the wave functions of these bands. And then that creates an electrostatic. So as soon as you change the number, you move away from neutrality. As soon as you change the number of carriers in these systems, you create a non-negligible electrostatic potential, which is not uniform. And what is interesting is that this potential, which is discussed here, in turn changes a lot the narrow bands. Because now you have an extra, so as soon as you increase, so the idea is you change the number of electrons, you create potentials which you do not create in other more conventional 2D systems, and these potentials, and the bands are very narrow, and because of that they're very fragile. So these potentials change complete. That's shown here. This is the initial narrow band as calculated initially in the theory works I pointed out to you at the beginning, and these are the bands once you dope the system. They totally change. And this is a unique case not encountered commonly in condensed matter physics. Bands which become wider when you turn on the interactions. As I mentioned before, the opposite is the more general situation. And I showed to you before our calculations, and that has been confirmed by many other calculations, and more importantly by experiments. These are STM experiments performed about 1.5 to 2 years after the initial discovery of the phase diagram of twisted bilayer graphene, and they all these STM experiments show peaks in the density of states. So definitely there are narrow bands, but these peaks are at least an order of magnitude wider than the bandwidth predicted by theory in the absence of interaction, which is a few MeVs. Typically, the bands you find in this system are no less than 30, 50 MeVs wide. And these are more experiments, compressibility experiments, which also allow you to measure the width of the band. And what that means is quite interesting. That means that there is an interaction in twisted bilayer graphene which you don't find in other systems. That if the band shape changes as you change the number of carriers, that means that you're somehow changing the hoppings between the Vanier orbitals associated to these bands, and that's called electron-assisted hopping. That was a topic widely studied by Jorge His way back in connection with the cuprates, and he suggested correctly that this points out our superconductivity. It's an interaction which cannot lead to charge density waves or magnetism or anything like that, but so the only other instability left is precisely superconductivity. We have worked on a much simpler model which shows these features, suggested by Liang Fu and Valentin Crepel at MIT. This is a kind of toy model for repulsive interactions, but which induce superconductivity because they include some kind of electron-assisted hopping. This is the simplest model you can think. You have electrons without spin in the honeycomb lattice near half filling and with a strong potential which bias one sublattice with respect to the other. And the simplest possible interaction in such a system is a repulsion between electrons at nearest neighbor sites. Nevertheless, that's enough to give you superconductivity. My colleague Misha Kasnerson pointed out that that was similar systems, not quite the same, were already studied in the Soviet Union way back. I was not surprised. But the thing is that at the end of the day, you have superconductivity, and we studied in detail which kind of superconductivity. The system like graphene has the Fermi surface is split into two valleys, and it's a superconductivity which is not trivial in the sense that the gap is not constant, changes sign, has opposite signs in the two valleys, but it's within each valley is finite. So it's a new kind of superconductivity, which we believe is probably related to the superconductivity found in twisted bilayer graphene. This is more arguments in favor of why you have attraction and what's the relation to, to the symmetry. And these are other calculations. As I said, this calculation is Hartree-like calculation in terms of an effective potential, which you build up when you do the system, explains the width of the band observed experimentally. And other insulating phase, in order to describe other insulating phases, you have to go from Hartree to Hartree-Fock. It's more complicated, but it's doable. And then you have many possible, besides, I mean, Hartree-Fock doesn't give you superconductivity, it gives you spin or valley polarized phases, or phases with a gap. And there are very many phases nearby with very small differences in energy from phase to phase. These are our calculations. This is, and by the way, these are the bands in twisted bilayer graphene as function of the Fermi energy. And you see, all of a sudden, when the central bands start to be filled, the bands change shape completely. And that's what I mean. It's very unusual in a condensed matter system. And the Fermi level continues to grow and grow, goes to the second central band, which are the important ones. And you see that again, the whole spectrum is changing as you increase the Fermi level. And then eventually the chemical potential moves into a higher band and things stop. Nothing, I mean, the bands behave rigidly, which is what you find in most systems. Okay, the Hartree-Fock calculations I mentioned to you before, the presence of many phases are very consistent with many experiments, which do suggest that there are many phases besides superconductivity hidden in twisted bilayer graphene. So at the end of the day, the Hartree-Fock description, except for not being able to say anything about superconductivity, does a good job of what happens in twisted bilayer graphene as far as the presence of interesting polarized phases of many types. Now, what about superconductivity? As I said, in heavy fermions and so on, the Hubbard model is a good starting point. But there is another way of, a more general way of studying superconductivity. There was a seminal paper way back after the theory of superconductivity by Walter Coulomb and Joaquin Luttinger, where they simply studied the electron gas. They noticed that when you put a charge in a regular metal, it creates a screening cloud with Friedel oscillations, and because of that, the screening potential sometimes becomes attractive. And they thought, well, maybe there is a kind of Cooper pair which can take advantage of these attractive regions, even when the potential created by a charge is repulsive towards when you put another charge of the same sign, it's repulsive on the average, but there are positions in real space where it isn't. And indeed, they found superconductivity in the electron gas only at incredibly low temperatures. However, this model, which probably explains well, for instance, the superfluidity of helium-3. And people have already studied this diagrammatic approach, which is more precise and more exact in connection with twisted bilayer graphene. These are more calculations, and these are other type of calculations. The generalization to twisted bilayer graphene is more complex, because basically the pairing associated to the Coulomb-Attinger mechanism is a pairing by electrons themselves, by electron hole pairs. But these electron hole pairs in graphene are at very low energy because the band is very narrow, and the plasmons associated to these partially filled bands are also at low energies. And not only that, but the phonons themselves overlap with these two spectra, unlike what happens in a conventional electron gas, which is shown here. There, you have a wide band, electron hole pairs have high energy, phonons have low energy, and they basically live in different worlds. Okay. These are our previous calculations, and these are our calculations. We put everything together, and this is a kind of more formal way of showing what we did, which is basically the recipe of Conan Latinger with emphasis on a particular diagram, which is more important in twisted bilayer graphene. But at the end of the day, definitely we got superconductivity. Thank you. And not very far from the experimental one. And definitely, as I said, this is superconductivity due to the long-range Coulomb interaction. So we think definitely it should be there no matter what. These are more details of how the superconductivity looks like. As I mentioned, it looks very much like the superconductivity one has in the toy model I showed to you before. This is the ordered parameter and so on. So, and it's interesting because it's non-trivial superconductivity, some kind of topological superconductivity. I think that's it. These are the main messages I wanted to convey. First, that the largest interaction, twisted bilayer graphene is a very interesting material indeed. Second, the largest interaction in twisted bilayer graphene is the long-range Coulomb interaction, and this is a simple estimate of how strong it is. This is the size of the moire, and this is the kind of self-energy of a quantum dot of that size with one electron in it. That means that the bands, which initially are narrow, stop being too narrow and are changed in a significant way by this interaction. Third, if you study pairing, superconducting pairing, through electron-electron interactions, you have to worry because there is a complex situation where the electron hole pairs, plasmons, and phonons overlap in the same region of parameter space. And finally, at the end of the day, this screen long-range interaction can lead to superconductivity. Thank you very much.
Thank you so much, Francisco, for your wonderful talk. It's open for discussion. I would like to ask a couple of questions. So one thing is, there is still a certain degree of uncertainty about electron-electron interactions, even in monolayer graphene. How much do you think this lack of knowledge is impeding our understanding of bilayer graphene?
It's a good question, and that's a bit on the eye of the beholder. At the beginning, most results in monolayer graphene, especially in the absence of a magnetic field, could be explained without invoking interactions at all. And many top experimentalists were skeptical about the role of interactions in single layer graphene until they found them. Because for instance, I was involved in that. In Manchester, eventually they found the so-called renormalization of the Fermi velocity, which is a very unusual process which happens in quantum electrodynamics. They found it in graphene in very clean samples, and then eventually they noticed that interactions were playing a role. But I agree with you that there are still facts, and there are even more interesting unknown parameters in monolayer graphene. One of them is the electron-phonon coupling. The deformation potential, you have values between like 5, 10 EVs and 30 EVs. And then if you turn the electron-phonon coupling into an electron-electron interaction, the effective electron-electron interaction mediated with phonons goes by the square of the deformation potential. So it can change by a lot. So, and then that uncertainty is transferred to twisted bilayer graphene. And for instance, there is a famous group in Maryland, Shankar Das Sharma, who claims that the superconductivity is basically due to phonons. But if you don't know very well the deformation potential, you are not very sure of which statements you can make. I think, as I say, it's on the eye of the beholder. The more we study theoretically twisted bilayer graphene, the more we discover that the initial estimates of everything are a bit suspicious because they didn't take into account the substrate, they didn't take into account strains, they didn't take into account many things which can change a lot these very fragile bands. So, and those things are not just sorted out. So it's a good question and still not fully answered.
Thank you. Questions from the audience?
Thank you very much for your amazing talk. I was wondering, I have seen recent papers in experimental physics that they are building 3-layer and quadrilayer graphene, and they are studying also the moire, this kind of moire patterns that will be.
But which system? Sorry again.
3-layer and also quadrilayer graphene.
Mentioned it, yeah.
And so the moire pattern will be richer. Can we find any new physical phenomena or new correlated phases in this kind of systems?
Actually, that's interesting because it turns out the tri-layer is a very special situation because you have one layer, then you rotate the other a little bit, and then the third layer has to coincide with the first layer. But it turns out, according to, for instance, Philip Kim and Pablo Jarillo Herrero, Harvard and at MIT, that it's very stable and it's very nice. Nobody knows for sure how many of the twisted bilayers work, depending on which experimentalist you ask. He or she will tell you maybe 1/5, maybe 20%, maybe 25%, maybe half. In the case of tri-layers, it seems that all of them work. All of them are superconducting. Let me see, because I mentioned that at the beginning. And I thought it was really unrealistic to expect that experimentalists could create such a systems, but they have been able to do it. And right now they have gone beyond three layers, and they have experiments on 4 and 5 layers with the same setup. You twist on one direction, then back, then forward again, and then back. I pass it. No, sorry, I had a slide, I showed it, but I don't remember if it's at the very beginning. No, it's somewhere here. Yeah. So these are the 2 tri-layer papers, and these are I didn't show you. There are now other papers with 4 and 5 layers, both from MIT and from Caltech, I think. And then and this seems to be for an experimentalist, the best samples in terms of reproducibility is for fabrication and so on. And now that in addition, at UCSB, Andrea Young in Santa Barbara has found superconductivity in untwisted multi-layers. The question is, where else can you find superconductivity in stacks of graphene layers? Actually, way back, there were claims of superconductivity in graphite. And it's not totally impossible that in graphite you have stacking defects. And maybe some of these stacking defects imply that there is some layer rotated by a small angle with respect to the neighboring layers. And you could have like a 2-dimensional electron gas embedded in a 3-dimensional graphite sample. So who knows?
Okay, thank you very much.
Thank you very much for the talk. I have one question, probably it's not really. My question is, I guess that the most stable energy corresponds to the system not twisted. Okay. Then when you twist this small angle, how you keep this structure?
That's a great question. Yeah, nobody knows. Okay, actually, I was in Manchester at the time. They knew that there was a way of creating moires by twisting, but they had seen graphene flakes rotating spontaneously back into the Bernal position. So they thought it was not the best way to get large moires. And definitely these moires are metastable at best. Probably there are strains at the edges. Some experimentalists have told me that they sweep bubbles to the edges of the sample and they pin one layer with respect to the other. Definitely, nobody tells you how many of these twisted layers work and how many don't work. And if you ask privately, everybody gives you a different answer. So, but definitely a lot of bilayers created exactly the same way at the end don't work. So, but nobody knows. As I said, this is a very good answer, and it's taken a long time for people even to ask it. But I suppose eventually somebody will look into it in detail.
Other questions?
Then, well, experimentally, I suppose that is in this way, but in theory, you can also investigate the situation in not one eclipsed layer on the other one, but you can shift one with respect to the other one.
Good point.
What happens in this case?
Okay. If you ask, it depends who. I mean, if you look at the lattice level, there is a small difference, but it is assumed, and there are good theoretical arguments for that, that at very small angles, where you have a large moire unit cell, that doesn't play a major role. Just a shift of keeping the angle fixed. So two samples with the same rotation, but some shift, some extra shift, should behave in very similar ways and have similar flat bands. That's the theoretical analysis, but it neglects spinning at the lattice scale, which nobody knows what will do. So there are still unanswered questions in that respect as well. And then there is the question of heterostrengs. All these samples have significant heterostrengs. By that I mean that there are strains which differ in the two layers. And those things change the unit cell, change the bands, change everything. But that's slightly different.
Okay.
So, Paco, why is the critical temperature in this twisted bilayer graphene or twisted layers always so low? Is it because the critical temperature? Is it because of the intrinsic strength or the quality of the samples?
Good point. There are two reasons for that. One is that you have very few carriers after all. I mean, you have flat bands, high density of states, but very few carriers. Because there are like a few electrons per 10 to the 12 square centimeters. That's very low for a metal. A metal has electrons per 10 to the 14 or 10 to the 14. Second, flat bands, even if they show attraction between electrons, need not be superconducting, because if you have a very flat band, you have something localized and you don't have phase rigidity. The claim is that the flat bands in twisted bilayer graphene, because they are topologically non-trivial, they can show, even if they are flat, if they become superconducting, they will show phase rigidity and then long-range superconductivity. And in addition, the critical temperature is growing a little bit. If you apply pressure, you increase the critical temperature by almost a factor of 2. And I think in the tri-layer, you also, I mean, that the critical temperature is increasing. So now, probably there are already samples going up to 3K or something like that. For a heavy fermion it's better than most heavy fermion superconductors. And then in the case of Andrea Young's samples without a twist, they are definitely, the critical temperatures are definitely very, very low.
Then, okay, this is a kind of school. Then, from this point of view, it's also useful to check or to explain a little what happens not in graphene, but in the other materials in which you can have also the twisting. You can have magnets, you can have also quantum spin liquids, you can have semiconductors. Then you should also have emerging properties in the other systems, I suppose.
I agree.
And then which are the most important?
There are both theoretical and experimental studies in twisted dichalcogenides, and also in large moires built by two dichalcogenides with almost the same lattice constant. The gap makes things different from graphene, because now the model is a bit different. It's the model of you start with a parabolic band, not with a Dirac band, not with two bands crossing. but you still have narrow bands, but those narrow bands are derived from an initial parabolic band, which is a different setup from the one I explained for graphene. Definitely, there are hints of correlated behavior. There's no evidence, to my knowledge, of superconductivity in these flat bands in twisted dichalcogenides. Also, molybdenum disulfide is actually a superconductor. And with respect to magnetism, I think people are starting to think about twisted. I mean, there is theory about twisted two-dimensional ferromagnets. But I'm not sure that if the people have done experiments.
But what do you expect from the point of view of the properties? If you, for example, you twist two ferromagnets, you expect some kind of chirality, you expect some kind of...
So, yeah. For instance, I have not followed too closely the theoretical literature. For instance, it will favor excitations in the form of skyrmions, not regular spin waves, but skyrmions. That because those skyrmions seem to tunnel better between the two twisted layers. But don't trust me too much because I'm not an expert.
Well, it's interesting, these possibilities.
Are there questions from the audience? I want to have another question, experimentally relevant, but maybe I can ask you. So these diagrams of the twisted layers, they never show anything between the layers.
Anything?
Between the layers. But when you're creating devices, you actually know that even below standard graphene, there is a lot of stuff. How much is that?
That's a good point. No, nobody knows. I have worked, for instance, on the shapes of bubbles, which are always there, and they're supposed to be hydrocarbons inside the bubbles. And I was told by experimentalists that these things have bubbles, so with some kind of dirt inside. What the bubbles do is a big mystery. And other types of, I mean, of course, all these samples are encapsulated. Actually, there's very little evidence, if any, of superconductivity in the samples they use for STM experiments, which by definition cannot be encapsulated. So encapsulation maybe takes care of some of this contamination and stuff which you may have. But that, to tell you the truth, nobody knows very much. People are happy that the systems work, I mean, that the systems have superconductivity, and nobody has paid a lot of attention to those issues.
Because there were quite a few reports of superconductivity in intercalated graphite. And you know, irradiated samples of C60 and stuff like that.
I agree. And maybe they had a point, because as I said, now people thought superconductivity and pure carbon compounds were incompatible. Clearly, that's not the case anymore. So one should revisit those experiments. I agree.
Thank you. No more questions? If not, let's thank our speaker again for the